Happy morning to all. Myself, Viji, Assistant Professor in the Department of Computer Science and Business System. Now I'm going to handle the course Formal Languages and Automata Theory. This is a flat course. The main course outcome of this subject is mainly to understand the concept of abstract machine and their power to recognize their languages. They are able to employ finite state machines for modeling and solving computing problems. Third one is to able to design context-free grammars for the formal languages. Fourth one is to able to distinguish between the desirability and undesirable problems. And also fifth one is we are able to gain a proficiency with the mathematical tools and formal methods. These are the course outcomes we can learn from this course, Formal Language and Automata Theory. In the Unit 1, we are going to learn about the finite automata, their main structural representation and their complexities. Then various automata theories like alphabet, strings, languages and problems related to that concept. Second part is non-deterministic finite automata, their formal definitions and their applications. Then text search and the finite automata with the epsilon transitions. So these are all the various topics we are going to see it in the unit 1. First of all, we should know about what is automata. Automata is a word that is a Greek word mainly which is meaning of self-acting. Automatons are the abstract model of the machines that performs the computation of an input and moving through a series of states. For example, we will have many states. If you are taking the examples like a washing machine, if you are sitting with the one particular state, it automatically move on to the further proceeding states and finally it will reach as one output. Like that, here also the automata is nothing but through the model of the machine that performs the computations of an input and they move through the many series of states that is known as automata. The first topic here is the finite automata. Finite automata is otherwise known as the finite state machines. For finite automata, we can able to represent it by the 5 tuples. So 5 tuples are nothing but Q, epsilon, transition symbol Q naught and F. Here capital Q is nothing but it is a finite set of states. Epsilon is a finite set of symbols, alphabets we are using in the automation. This tau is nothing but a transition function. Q naught is the initial state from where any input is processed. Capital F is nothing but a set of final states it is n-most stage, n stage, that is capital F. For example, consider this example. We have taken the 3 states. One state is a state A, second state is a B, and the double circled state is a final state or the end state. Here we have the two input symbols. One is a 0 and other is a 1. From A state, if we give the input 0, it again goes to the same state A. If you are giving the input 1 from the A state, it moves on to the next state, that is B. So for 0 and 1, considering this state A, it moves to the 2 states. One is the same state and other is the B state. From B state, when you give the input 0, it moves on to the final state. When you are giving the input 1 from the B state, it moves on to the input symbol A state. So, in the final state also, if you give the 0 output at the end of the state, it move on to the B state. Then if you giving the 1 as the input in the final state, again, so once again, it will be there in the final state itself. This is a basic examples for the finite automata. So here we are representing the various number of states and the two inputs. So whenever we are giving the input, it like a series of states. It's moved from one state to another, and finally it reaches the end state. The circle here, it represents the name as a states. The arc labels, that is, for example, these are all the circles. These are all the arc symbols. It represents the input alphabets that shows the transition from one state to the other state. The initial state is represented by the empty single incoming arc, and the final state is indicated by the double circles. Here, what are all the various states we are having? A, B, and C. Summation is nothing but it is an input symbol, either 0 or 1. Q naught here is the initial state. In our example, we are taking A as the input or initial state. Capital F is nothing but the final state. Here in the example, we are taking the C as the final state. The next one. This is a basic structure of the finite automata. Each and every inputs are being taken through the tape as the input variables. Through the storage or data structure tape, we are getting our input strings. By using the finite control, each and every input strings or input alphabets are being read or write, and then it fetched through the finite memory. This is the structure of the finite automata. The basic structural representation of a finite automata, it can be represented in two ways. One is the transition diagram and second is the transition table. So the previous one, the example we have seen is the structure of using the transition diagram. That is the state and arc circle diagrams and the state diagrams. The second is the transition table. Here, as the rows and the columns, the states are as the inputs are given in that column wise for each and every input variable 0 from one state to other state. If you give the input 0 from A, it moves on to the A state. If you give the input 1 from the A state, it moves on to the B state. Like that, for each and every state, it fetches one input and moves from one state to the other state. Here, this arrow mark, this represents the input symbols. Here, the arrow mark, star symbol represents this C as the final state. This example for the transition table. So, transition diagram, we have already seen that each and every states each and every states are represented by the capital Q and they are represented by the circle, and each and every input symbols are being directed edges from one node to the other node, that is one state to the other state. This can be represented by using the transition symbol. This is known as the transition symbol tau from the input state with the input data, that is the state comma the input variables, it moves on to the next state. Like this way also we can represent the transition of one state to the other state. In the start state, there is no arrow with no source. Accepting states are the final states. They are indicated by the double circles. The next one here, in the sample example, each and every states are represented by the single circle. And if you are giving the input, it is represented through this arrow mark or like an arc like symbol also. This indication of the arrow with one circle, this represents the start state. If it is a double circle, it represents the final state. In transition also, transition table as an example, columns corresponding to the input symbols and the rows are corresponding to the states. The entries are that are corresponded to the next state. For each and every input, it moves from the one state to the other state. That is also represented through the rows and columns. The accepted state is denoted by the star symbol. Here we are represented through the star symbols. Like this way, this one is the example of the transition diagram. This table representation is the example for transition table. The next topic is the Chomsky normal form. Chomsky normal form is nothing but through which we can hierarchically we can arrange the languages those the machines are accepted. So basically we will have the regular language. The next level is the context free language. Third level is the context sensitive language, and the fourth level is the recursively enumerable language. What is the meaning of these one? First, this recursively enumerable is comes under the type 0 grammar. This is the example. This type of grammars can be taken as an example for the Turing machine automation methods. Turing machines example, we can take the type 0 grammar that are recursively enumerable languages. Second one is type 1 that comes under the context sensitive languages. Here linear bounded non-deterministic Turing machines are coming under this method. The next one is type 2 grammar. These context free languages will comes under this concept. Here under which we will consider the push down automata. So the last one is type 3 grammar. They are using the regular languages. For such type of type 3 grammars, we can able to do the finite state automation. This is a basic Chomsky normal form where based on the generation of the machines, the languages corresponding grammars also considered. The next basic things we have to learn through this formal languages. First one is alphabets. Alphabets are nothing but a finite collection of the symbols. Symbols, so for example, it may be in alphabets or numerical terms like that. Each and every collection of symbols they are called as alphabets. Example, A B can also be an alphabet. 0 1 also be an alphabet, or from small letter A to the small letter EZ. Every lower cases alphabets are lower case letters are considered as the alphabets here. The second one is a string. Strings are nothing but we are talking about the alphabets. All the finite sequence of symbols comes under the strings. Finite sequence means is collective of the alphabets are known as string. For example, here A separately it is also called a string, or together with a B combinations or mixture of any other alphabets, they are known as strings. Here, infinite number of strings can be generated. There is no limit to generate. We can generate the infinite number of strings through the alphabets. Like such a way, we can able to gather various input strings from the collective alphabets. So we have learned about alphabets and strings. Third one is the languages. Languages is nothing but we have already learned about the various type of grammars, type 0, type 1, type 2, like that. Here in such a way, collection of a related or appropriate strings. So group of alphabet is known as a string, and a collection of the appropriate strings are known as languages. Here we have given the two examples. One is these are all the various set of strings. So, for example, if you are going to collect these all in a one set of group, then it is known as a language. The set of all strings over A, B, C having AC as a substring, like that we can able to have the many related strings that are related to that appropriate strings, then these set of collections are known as languages. By using these languages, we can able to apply the various set operations like we have learned in the mathematics set languages or set algebra. Here the union operation, concatenation operation. So we can learn about what is clean star and clean closure, what is complement. Everything you know in maths, union is the joining of the two things. Concatenation is nothing but the common things in both the strings. Clean star and clean closure, we can see it in the next slide. Complement is nothing but apart from the inputs, what are all the overall universal sets contained apart from the input string, they comes under the complement. Difference is nothing but intersection of the both the things removing, and particularly from one set we are getting the input, that is known as difference. So such a way we can able to calculate the many set operation by using the languages. So now we have to know about what is clean star and the clean closure. Clean star is nothing but clean star is a unary operator. It is a set of symbols. For example, if you are taking the input 0 and 1, then summation of the whole power star symbol is known as a clean star. So here the what are the various type of inputs we can generate is one, this symbol is known as epsilon, that is the empty symbol. 0, 1, 00, 0, 1, 1, 0, 1, 1, the various two-digit inputs or three-digit inputs we can able to generate through only this two inputs, 0 and 1. Such a way, if you are generating along with the empty string, that is known as clean star. So in single digit generations are not 0, 1, double digit generation this one is a three digit generations. So clean closure is denoted by the language L power star. Clean star we can able to do as I said before, we can do many set operations. One is union operations. For that example we are taking L0 language, L1 language and L2 language. We are going to union do the union operation. So for that, L0 is a empty state, L1 is a single digit strings we have generated, L2 is a two digit generate, two digit strings we are generated. So here we are going to gather all the strings together. This is known as a clean star. So along with the summations, we are going to gather or join all the inputs that are presented in the various languages are known as clean star. Here the clean plus is related to the clean star, but here we don't have the epsilon symbol. So it starts only with the 0 or 1, that symbol, but we don't have the epsilon symbol here. But in the clean star, we will have the empty symbol, that is the epsilon symbol. Here in the clean plus, we don't have any epsilon string. All the elements are presented in clean plus. Here, under the finite automata, we have two types of finite automata. One is the deterministic finite automata, or otherwise it is known as deterministic finite machine. The second type is non-deterministic finite automata, or it is otherwise known as non-deterministic finite machines. Now we are going to learn about DFA and the NFA. Here, as I said, it is divided into two types. One is the DFA and the NFA. Coming to the DFA, DFA is represented by the state diagram. Here, the vertices represents the states, the arcs labeled within the input alphabet that shows the transitions in considering about the initial state and the final state. NFA, it is also represented by the 5 tuples. One is a capital Q, that is a set of finite states. Epsilon, that is a finite set of symbols. They are called as alphabets. Here the tau symbol that represents the transition functions, where tau, here q into summation that represent 2 into q. That is the power set of q has been taken, because in case if it is a non-deterministic finite automata, the transition can occur to any combination of q states. For that only we are representing the power set of q. Q naught is nothing but the initial state from where any input is processed, starting state. Initial state is nothing but a starting state. Capital F is nothing but the set of finite states. Here also we are going to represent the graphical representations. The starting state is represented by a single arrow, and each and every arrow mark that represents the input symbols given to the each state. When one input is given to other input, it moves on to the next state. Here for non-deterministic we have not only one input symbol, it can have many input symbols, or one or two input symbols can move on to the one state to the other. This is one example for NFA. Such way in transition diagram also, not only the one input from one state to other, it can have many or two or three inputs, output states can be get brought from the non-deterministic finite automata, NFA. But in DFA, we will have only one to one state. Here, one to many state. Within that, we are closing these concepts of basic concepts of the formal language, the basic contents, alphabet, strings, and the languages, Chomsky normal form, and we have learned about two type of finite automata: deterministic automatic finite automata and non-deterministic finite automata. Thank you. We can see it in the next slide.